Hello again. In this lesson, we're going to be factoring expressions. Don't let those words be meaningless to you. Factoring is something we've done before with numbers. If we had the number 24, we can break it down into two numbers that multiply to 24, like 2 and 12. 2 and 12 are factors of 24. So are 3 and 8, 4 and 6, 1 and 24. They're numbers that multiply together to give us that. That's what factors are. So let's look at this example, this model here. We've got 2 times 5 and 2 times 3. Giving us these 2 blocks of 5 and 2 blocks of 3. Well, if we rearrange it, putting the 5 and 1 5 and 1 3 together, we have a 5 and 3 block, and then we have 2 of them. So this kind of looks like what we've been doing in the distributive property. We've been kind of going from part B to part A, but now we're going from part A to part B. So are these equivalent? Yes. We know that from the distributive property, which we've been using already. That's kind of the relationship here. But the heart of this lesson is going backwards in that relationship. Let's see what it looks like again one more time. This time with variables. So we've got 2a, we've got 2b added together, but if we group them as a and b, that's a and b together, 2 of those blocks. So are these equivalence expressions? Yes, we can even use the distributive property to kind of convince ourselves of that. 2 times a and 2 times b gives us 2a plus 2b, same as what we have on the other side of our equal sign. So again, we're going backwards. What I boxed in there, that's what we're really looking for as the answer. All right, let's look at 3f plus 3g. If I look at their coefficients have something in common. They both are factors of 3. So both of these terms, the 3f term and the 3g term, have a factor of 3. So we can pull that out and leave that as 3 times the quantity f plus g. If we have 6x plus 9y, 6 and 9 both have 3 in common as well. So what would be left? What would you have to multiply by to get that 6x? 3 times 2 would give us 6, and the x kind of comes along for the ride. What about the 9? 3 times 3 gives us 9. Y comes along because it's another factor. So what about 3c and 11c? The coefficients have nothing in common other than 1. But there is still a common factor. That common factor is c, because c here is a factor. c is being multiplied by 3, c is being multiplied by 11. So c is a common factor. So c can come out and be on the outside of the distributive property, and inside would be 3 plus 11 left over. Now you might be thinking, why didn't we just take 3c plus 11c and get 14c? Totally correct, that is combining like terms, but we were trying to write an equivalent expression. This is kind of another justification for it, because we could pull out that c, have 3 plus 11 is 14, and yes, c times 14 is 14c. We are combining like terms. All right, the expression 24b plus 8. The coefficient of b and the constant at the end, they both have a GCF of 8. 8 goes into both of those. So we can rewrite this as 8 times something. What's the other something? Well, 8 times 3 gives us 24, and if we put a b there, that's going to give us 24b. And then 8 times what is going to give us 8? You need to make sure you remember that 1. It's easy to forget. Lots of students will forget that, but think about it. If you did the distributive property, you'd need to create that 8 back there. If you left nothing there, you wouldn't get 24b plus 8. We would just get 24b. So that 1 there needs to be there because we must leave behind the other factor that multiplies to give us our original expression. All right, practice makes perfect. Let's do some more examples. Okay, we look at 7x plus 7y. In common is a 7, leaving us with x plus y. 15g and 20h, just looking at the coefficients, there is a 5 that goes into both. G and h have nothing else in common. So 15 times 3 is 3g. 5 times 4 is 20, so we have 3g plus 4h. 6 comes out of 18n plus 42, leaving us with 3n plus 7n. 3 can come out of 38 plus 39, leaving us with 10a plus 13b. Here we have a common factor of f, leaving us with 11 plus 15 inside. F comes out. These are equivalent expressions. So h can come out of 18h plus 13h, leaving us with 18 plus 13. Here an 11 can come out. Do not forget that 1 at the end. 5m plus 1 must be left over. Then 7 can come out of here. This time we have a 1 in the front, leaving us with 7 times the quantity 1 plus 8. Y. All right, so I've told you that they're equivalent. Let's kind of convince you a little bit more by plugging in some numbers. So I plug in values to two expressions. Let's see how they work out. So in the first half, we get 102. In the second half, we get 3 times 34, 102 again. So you can see that in factored form or original form, we still got the same answer when we plugged in values. Try it again here in the second example. Plug in 6, we get 72. We plug in 6 on the other side, we get 72 again. All right, here, if we plug in 10, we get 142. And on this side, we get 7 times 10 plus 1 is 71. All right, 142 again. Factored form, original form, we're still getting the same results every time. So those must be equivalent expressions, because every time, no matter what value we get, we're going to get the same results. So yes, this will work with all values because the expressions are equivalent. All right, so how can we use this information? By dividing terms by their GCF, we can rewrite expressions as a product of their GCF and the remaining factors. That's the whole goal here, is rewriting an expression as a product where the GCF is one of those two factors. All right, so here they've given us the remaining factor, and they're asking us to identify what the GCF was. So between 4 and 12, 4. Between 35 and 55, 18 and 9, 9. 32 and 8, 8. 100 and 700 is 100. So how do we find the missing number? We were looking for the GCF. What number goes into both coefficients in both terms? So you can think of this the other way. You might be looking for like what number kind of completes the distributive property here. So if we have x plus 7y here, well, it has to get us to 100x and 700y, so I need to be multiplying by 100 there to kind of go backwards. All right, here we're going to prep you for some more advanced examples. In 5 through 8, we're looking at what is the integer that goes into the coefficients of each expression. So in 5, 9 goes into both of those terms. In 6, 7 goes into both. In 7, 6 goes into both. And into 8, 5 goes into all three. Now let's look at variables. What goes into all three, both terms variable-wise? This first one has none. So not all of them will. But here we have expressions that are basically 7 times x and 21 times x. They both have an x that they can give, an x factor in common. When we have x to the 6th and x to the 3rd, that's 6x factors and 3x factors, so they both have 3x factors they can give. 15x cubed, 25x squared, and 55x all have at least one x in common to give. All right, now we're taking those two pieces together. We look at the integer and the variable together to give us 9x plus 5, 9 times the quantity x plus 5. Here if we look, 7 is the integer, x is the variable, that's our GCF, times x minus 3 is going to be the leftover piece inside here. In 15, we had 6 and we had x to the 3rd. Now we're basically subtracting 3 x's away from each of these expressions here. So x to the 6th becomes x to the 3rd. And x to the 3rd is gone altogether. And then we're dividing the coefficients. So 5 comes out, x comes out. That's going to leave us with 3. We took away an x, so now we have x squared. We took away an x here, so we just have x. And we took away an x here, so we have no x's left. And that's our expression. So we can practice some more of these in class, but let's look at 23 where there's two variables. So look at the coefficients first. 3 goes into both. Look at the variables second. So we have 3 x's is the most they can both give. Y's, they both have 2 y's at least. So what's going to be left over? Just a 1, and x is going to be left here. We took out all the y's and all the coefficients basically. 5 goes into 3 goes into 15 5 times, and 1 y is left over. If there's a leading coefficient of it that's negative, we're going to pull that out. So instead of pulling out 2 from 2, 4, and 6, 2, 14, and 6, we're going to bring out negative 2. And we're also going to bring out an m, so that's going to take away 1 m from each. So that's going to be m to the 3rd, and oops, I should have made that a subtraction here, because it's going to basically change the sign of everything inside. So it's going to be negative 7 that we're going to need. So negative 7m, and then plus 3. All right, so now we're going to look at some area model examples. Here we have rectangles with the dimensions given. Area here is 20, area here is 7m, area here is 3a. Don't know what that was. Area here is x squared. X times x is x squared. 4 times x is 4x, and this other rectangle is 4 by 3, so that's 12. So that's the expression 4x plus 12. So this is another visual for how you can see distributing. And this is important because we're about to go backwards here. So a line segment, 2 pieces, x and 9 would be the total. If this was 3, 3 plus 9 would give us 12. We don't know what it is, so we're just adding x to 9 instead of adding a specific number. So x plus 4 here, a plus 2 here. Here we have just the rectangles pushed together, 5x and 35. That's it written as a sum. Conversely, we also could have written it as a product, 5 times the quantity x plus 7. So inside here we have x squared plus 12x. So as a product, we're taking x as a 1 factor times x plus 12. As a sum, we're writing x squared plus 12x. Here, a squared and 8a. So as a product, a times a plus 8. As a sum, a squared plus 8a. So let's just look at a couple examples down here. We can save some of them for class. A times a is a squared, and a times -1 is negative a. So a squared minus a. Here we have 3. M times m is m squared, and 3m times 2. Multiply the coefficients to get 6m as your written as a sum. All right, now we're going backwards. We have the areas written out as a sum. We need to find the other term here. So x plus 4 is our other factor here. So 5 times the quantity x plus 4. This is another way to help us visualize how to be factoring, how to be going backwards. All right, so that's going to be a 6, that's going to be an x to give us our 6x here and still give us our 48 there. So how can we write it as a product? 6 times the quantity x plus 8, or 6x plus 48 written as a sum. Here they gave us the inside pieces. They tell us that must be a 5 as the GCF. So 5x plus 35 is going to tell us it has to be an x there, it has to be a 7 there. So we're again looking for how can we find out what that other factor is inside. That's our answer, 5 times the quantity x plus 7. So 2 times what will give me 2x plus 12, x plus 6 is the other factor. All right, so here we have to find the GCF is 3, so 3 goes out there. 3x minus 21 they gave us, so x minus 7 must be the other factor. It's important to make sure we make that a minus there, so we make our other factor x minus 7. So some other examples for us to continue practicing in class. Let's do one of these ones without the visual aid. 4 times what gives me 4x, 4, and our other factor is x minus 4. All right, so we can look at lots more practice here. Let's look at number 3 because it's got an x squared here. What times what will give me x squared? X times x will give me x squared. So that's x is one factor, x plus 10 is the other factor. So written as a sum is x squared plus 10x. So let's do one of these examples down below. Let's try on this page where we're doing some factoring, but pulling out just a factor, not a greatest common factor. So here in the first one, they just brought out a 3, not the GCF. There's still something in common between x squared and 5x. If we look at the part B, they pulled out an x. Now that's not the greatest common factor. There's still a factor of 3 that could have come out. Here they finally pulled out the GCF, and that leaves us with x plus 5. So which of these is the best? C is the best because it pulls out the greatest common factor. And when I say pulls out, we are dividing each term by that, but it's kind of coming out front, so you will hear math people calling it pulling out at front. All right, we will practice some of these more in the class, but let's just jump down to something that's a little bit more advanced so you can see that coming. So here we have 40 and 36. 4 goes into both of those. X squared and x to the third both have 2 x's, so x squared can come out. So what's left inside? 4 times 10 would give us 40, and all the x's are gone. And then 4 times 9 would give us 36, and there's 1 x left over. So that is the answer we're looking for on that example. Here again with 2 variables, 10 can go into both, leaving us, and then we can pull out a 5 x's and y to the third. Basically looking for the smallest exponent in each term. So that we need to multiply by 4 to get our first term and 9y squared to get our other term. The y squared is really coming from the fact that there was y to the fifth and now there's only we took out y to the third, so we have left with y squared.